I wanted to take a moment to just kind of put it all together for the rules that we've learned here for these kinds of trigonometric integrals. So if you've got sine and cosine, this is what you're going to do, right? You've got two possibilities, any odd power. Doesn't matter if it's sine or cosine or both. Any odd power, take 1 sine cos from that odd power to be your du. The other, then the other is your u. Okay? If all powers are even, you just start cursing and use the half angle formulas as many times as necessary. For secant and tangent, but also I didn't do any, if you do see cosecant, cotangent, it's the same thing. Right? Because the formulas for cosecant and cotangent for the derivatives are the same as secant tangent, only there's a minus involved. So when you do cosecant cotangent, you have to remember that when you take the du, there's an extra minus. But other than that, the strategy is the same because the patterns are the same. I typically won't ask you to do cosecant cotangent because it's the same thing, but there might be one on the website or something. Right? So for these guys, you have the following two possibilities. So these are two possibilities, right? 1, 2. So secant tangent. First possibility is even power of secant. If you have even power of secant, you save 2 of them for your secant squared, your du, which makes you your tangent. Okay, and then no matter how many more there were, then you can change the rest of those to tangents. Your second possibility is odd power of tangent. Okay. So that would be du would be secant x tangent x dx. Oh, I hope you can see that here. Boop, boop, boop. There we go. And u ends up being secant x. Unlike the situation over here, though, we haven't figured out every possibility because you can imagine you have an integral with an odd power of secant and an even power of tangent, you know, something like tangent squared x secant x, something like secant cubed x tangent to the 4th x. Okay. If this happens, all bets are off. 3. Other possibilities. So for other possibilities, I'm not going to ask you to do them, basically, because everyone is different. Usually you just have to try stuff, so try some fancy integration by parts. A lot of times with these, what will happen is it's going to be one of those repeating ones. If after you do 2 integration by parts, you get the same thing back, but with a different sign, and you put it over on the other side. You can do that. Sometimes you have to do something really strange, where you have to know some special substitution or something that makes it work. So these are all weird. I'm not going to ask you to do them. There will be an example in the extra materials, so you can see kind of some of them in the book. They have a couple done, but I'm not going to ask you to do them on a test or a quiz because it's very much trial and error, very random for these guys. There is one that comes up all the time that is of this other possibilities, and that is secant. Okay. Now, I'll do this for you now, show you how it's done. It's done with a very clever trick. And that's with some of these other ones. You just need to know what clever trick, or just keep working at it till something happens. So yeah, they can be really awful. Secant does have a special trick, but I also put it on your table of basic integrals because it's like there's the one thing that you just kind of can just use that after we've done it here. I don't expect you to remember exactly what this trick is. It's not that hard to remember, it's just weird. Okay? So this special trick, just a thing that somebody figured out to get this to work out so that you got the antiderivative. And what it is that you multiply top and bottom by 1 in the form of secant x plus tangent x. So I don't know who figured this out. Someone way back when. I should probably look that up. But let's look up what this looks like then. This looks like secant squared x plus secant x tangent x in the top. And this looks like, I'm actually going to, well, write it the other way. Tangent x plus secant x in the bottom to make it more clear. Okay? Now my bottom is this. And this is the derivative of that. This is the derivative of that, right? So now it can do a u substitution where I do u is the bottom, then the derivative of that bottom is the top. So that's the kind of thing I'm talking about. There's some weird trick. Would I expect you to come up with one of these sort of crazy tricks? No. Would I expect you to be able to look at it on a chart and use it? Yes. Okay. So this is our du. Then obviously this becomes integral of du over u, which is natural log of u. But what was my u was this thing. And often I just remember it as secant x plus tangent x. I don't know why. That's how it's often written on. It doesn't matter. Tangent, secant, whatever. So that's how that one comes up. Feel free to just use it without any work because I left it on the table of basic integrals for that reason.